The Vajont Dam represented the culmination of post-war Italian engineering ambition, embodying a design philosophy that prioritized structural perfection within carefully defined operational parameters. Completed in September 1960, the 262-meter concrete arch structure stood as one of the world's tallest dams, engineered to harness the seasonal flows of the Vajont River for hydroelectric power generation. The facility's technical specifications reflected the era's confidence in computational analysis and material science. A double-curved, thin-arch design that distributed hydraulic loads through geometric precision rather than mass. The dam's structural concept emerged from established principles of arch dam engineering, where the curved concrete shell transfers water pressure laterally into the canyon walls rather than relying on gravitational resistance. This approach demanded exceptional foundation conditions and precise geometric calculations, both of which the Vajont site appeared to provide. The narrow gorge offered solid limestone abutments capable of absorbing tremendous lateral forces, while the reservoir basin promised a storage capacity of 150 million cubic meters at maximum pool elevation of 722.5 meters above sea level. Engineers approached the project within a framework that treated the surrounding geological formation as a stable boundary condition. The limestone and marlstone sequences of the Vajont Valley had been assessed using standard geological surveys that focused primarily on foundation stability beneath the dam structure itself. These investigations confirmed the bedrock's capacity to support the arch loads and resist sliding, satisfying the primary design requirements for dam safety. The assessment methodology reflected contemporary practice, detailed analysis of the immediate dam site with broader geological reconnaissance of the reservoir area. The design philosophy embedded within the Vajont project assumed that geological hazards, if present, would manifest as gradual processes observable through monitoring and manageable through operational adjustments. This assumption aligned with established dam engineering practice, where geological risks typically involved foundation settlement, abutment movement, or gradual slope degradation, phenomena that develop over years or decades with clear warning indicators. The possibility of rapid, massive geological failure was considered outside the credible hazard spectrum for a site that had passed standard geological screening. Operational procedures for the Vajont facility reflected this design confidence. The reservoir filling protocol, initiated in February 1960, followed conventional practice for large dams, gradual impoundment with monitoring of structural response and foundation behavior. Instrumentation focused on dam performance parameters, concrete stress, foundation movement, seepage rates, rather than comprehensive slope stability monitoring throughout the reservoir perimeter. The control philosophy emphasized maximizing power generation efficiency while maintaining structural safety margins, with reservoir levels managed according to seasonal demand and inflow patterns. The facility's instrumentation architecture embodied the ERA's approach to dam monitoring, extensive measurement of structural parameters combined with visual observation of obvious geological changes. Concrete stress gauges, settlement monuments, and seepage collection systems provided quantitative data on dam performance, while periodic geological reconnaissance monitored for visible slope movement or rock deterioration. This monitoring strategy assumed that significant geological hazards would produce observable precursors detectable through routine surveillance methods. Training for operational personnel emphasized structural safety and power generation optimization, with geological hazards addressed through general guidelines for visual observation and reporting. Operators were trained to recognize signs of foundation problems, excessive seepage, or unusual structural behavior, but received limited instruction in slope stability assessment or landslide recognition. The operational mental model treated the reservoir as a passive container with the dam as the primary engineered component, requiring active monitoring and control. The regulatory framework governing the Vajont project reflected Italian dam safety standards that prioritized structural integrity and flood control capacity. Design approval processes focused on structural calculations, foundation analysis, and spillway adequacy, with geological assessment treated as a preliminary screening activity rather than an ongoing operational concern. Safety verification centered on the dam's ability to withstand design flood events and seismic loads, with reservoir-wide geological stability, considered a site selection issue resolved during initial feasibility studies. This regulatory approach aligned with international dam engineering practice of the period, where geological hazards beyond the immediate dam foundation were typically addressed through site selection rather than ongoing risk management. The assumption that proper site selection eliminated geological risks shaped both design standards and operational protocols, creating a framework optimized for structural engineering challenges while treating geological systems as stable environmental conditions. The design assumptions embedded within the Vajont project reflected broader engineering confidence in the controllability of large-scale infrastructure systems. The facility was conceived as a precisely engineered mechanical system, arch dam, spillway, power plant, operating within a predictable geological environment. This conceptual framework treated the surrounding mountainsides as fixed boundary conditions rather than active geological systems capable of rapid large-scale change. The instrumental logic governing reservoir operations embodied these design assumptions through measurement systems, focused on dam performance rather than geological monitoring. Water level gauges, power generation metrics, and structural instrumentation provided operators with detailed information about the engineered system's behavior, while offering limited insight into geological processes occurring within the reservoir basin. The information architecture assumed that geological hazards, if present, would manifest through observable effects on dam performance or visible changes detectable through routine inspection. Critical design vulnerabilities existed within this framework, though they remained hidden beneath successful structural performance and regulatory compliance. The assumption that geological assessment could be treated as a one-time site characterization activity rather than an ongoing monitoring requirement created a blind spot in operational awareness. The focus on dam-centric instrumentation provided comprehensive data on structural behavior while leaving geological processes largely unmonitored except through visual observation. The procedural framework governing emergency response reflected these same design assumptions, with protocols focused on dam safety and downstream flood protection rather than geological hazard management. Emergency plans addressed scenarios involving structural failure, spillway inadequacy, or extreme flood events, but provided limited guidance for geological emergencies originating from within the reservoir basin. The operational mindset assumed that geological processes would provide sufficient warning time for deliberate response, allowing for measured decision-making based on observable precursors. These design assumptions created a systematic vulnerability that would prove decisive under conditions the engineering framework had not anticipated. The Vajont Dam functioned exactly as its structural specifications demanded, performing flawlessly under loads far exceeding design parameters. The geological system containing the reservoir operated according to its own physical laws, governed by stress conditions and failure mechanisms that existed independently of the engineered structure. The intersection of these two systems, one precisely controlled, the other inadequately understood, established the conditions under which engineering excellence could coexist with catastrophic system failure. The latent conditions that would enable the October 1963 disaster were embedded not in engineering incompetence, but in the boundaries of the engineering assessment framework itself. The design philosophy that produced a structurally perfect dam also created the analytical blind spots that prevented recognition of the geological hazard developing within the reservoir basin. Perfect execution of an incomplete understanding had established the conditions for an unprecedented failure mode that challenged fundamental assumptions about engineered system control and geological predictability. The operational context surrounding the Vajont Dam contained multiple latent failure conditions that existed independently, before converging into a singular failure pathway. These conditions were not the result of negligence or incompetence, but rather emerged from the systematic application of standard practices within a geological environment that exceeded the assumptions underlying those practices. The human-machine interface design, monitoring protocols, and organizational decision-making structures all functioned as intended while inadvertently creating conditions that would amplify rather than mitigate the developing geological hazard. The first significant latent condition lay within the geological monitoring framework itself. While extensive instrumentation monitored dam performance, geological surveillance relied primarily on visual observation, supplemented by limited instrumental measurement. This monitoring strategy reflected standard practice for dam operations, where geological hazards were typically expected to develop gradually with clear visual indicators. The monitoring protocol assumed that significant slope movements would be detectable through routine inspection and would provide sufficient warning time for corrective action. However, the geological characteristics of Mount Tuosi created conditions where this monitoring strategy was fundamentally inadequate. The limestone and marlstone sequences contained ancient clay layers that acted as potential sliding planes under specific stress conditions. These geological features were known from construction-era surveys, but their significance for long-term slope stability under varying reservoir conditions had not been fully evaluated. The presence of these clay layers created the potential for deep-seated slope failure mechanisms that could remain undetectable through surface observation until movement became irreversible. The reservoir operation strategy introduced additional latent conditions through the relationship between water level management and slope stability. Standard operating procedures prioritized power generation efficiency and flood control, with reservoir levels managed according to seasonal patterns and electrical demand. The operational framework treated water level as a controllable variable for optimizing system performance, without systematic consideration of its effect on slope stability throughout the reservoir basin. This operational approach created a systematic bias toward reservoir-level manipulation that inadvertently stressed the geological system. Rapid reservoir-level changes, implemented for operational efficiency, induced corresponding changes in groundwater pressure within the surrounding slopes. The operational logic that emphasized quick response to power demand fluctuations conflicted with geological processes that required gradual adjustment to maintain stability. The reservoir became not simply a water storage facility, but an active geological loading system whose operation could trigger slope failure mechanisms. Personnel training and organizational culture contributed additional latent conditions through emphasis patterns that prioritized certain types of technical knowledge while de-emphasizing others. Dam operations training focused extensively on hydraulic engineering, electrical power systems, and structural monitoring, reflecting the primary functional requirements of a hydroelectric facility. Geological hazard recognition received limited emphasis, treated as a specialized skill set outside normal operational competence, rather than a core safety requirement. This training bias created systematic knowledge gaps within the operational workforce. Personnel capable of detecting minor changes in dam structural behavior through instrumental data might simultaneously fail to recognize significant geological warning signs visible during routine facility inspections. The organizational knowledge structure assumed that geological hazards were the responsibility of specialized consultants rather than operational staff, creating dependency relationships that delayed hazard recognition and response. The alarm and alerting systems reflected these same prioritization patterns. Sophisticated monitoring networks tracked dam performance parameters with high precision and automated alert capabilities, while geological monitoring relied on manual observation and subjective interpretation. This instrumentation hierarchy created an information asymmetry, where operators received immediate quantitative data about engineered system performance, while geological hazard information arrived through less definitive, more subjective channels. The psychological impact of this information asymmetry proved significant in shaping operational decision-making patterns. Precise instrumental data about normal dam performance provided strong psychological confirmation that the facility was operating safely, while vague or subjective geological observations could be rationalized as normal operational variations. The human tendency to weight objective, numerical data more heavily than subjective observations created a systematic bias against geological hazard recognition even when warning signs were present. Organizational decision-making procedures contained additional latent conditions through their emphasis on consensus and documentation for major operational changes. While this approach prevented hasty decisions and ensured proper consideration of complex technical factors, it also created procedural delays that conflicted with geological emergency response requirements. The administrative framework optimized for deliberate engineering decisions proved inadequate for rapid response to geological hazards requiring immediate action. The regulatory environment contributed to these latent conditions through oversight frameworks that emphasized structural compliance while treating geological hazards as resolved issues following initial site approval. Regulatory inspections focused on dam performance, maintenance, compliance, and operational procedure adherence with limited attention to ongoing geological hazard assessment. This regulatory emphasis reinforced organizational priorities that treated geological monitoring as a secondary concern rather than an ongoing safety requirement. Communication protocols between operational staff, engineering consultants, and regulatory authorities created additional systematic delays in hazard recognition and response. Information flow patterns optimized for routine operational coordination proved inadequate for geological emergency management, where rapid information sharing and decision-making were essential. The communication architecture assumed that geological changes would develop gradually, allowing time for deliberate consultation and consensus building. The most critical latent condition emerged from the intersection of instrumental precision and interpretive ambiguity in slope movement assessment. The limited geological monitoring systems in place could detect slope movement but provided ambiguous information about movement significance and failure timing. Small measured movements could represent either normal geological adjustment or the early stages of catastrophic failure, creating interpretation challenges that existing protocols did not adequately address. This interpretive ambiguity created a systematic bias toward conservative interpretation of geological data, where measured slope movements were attributed to normal geological processes rather than failure precursors. The operational framework encouraged operators to continue normal operations unless clear evidence of immediate danger was present, but the geological monitoring systems could not provide the level of certainty required for definitive hazard determination. Personnel were trapped between incomplete information and procedural requirements for certainty before implementing major operational changes. The relationship between operational confidence and geological uncertainty created additional psychological pressures that influenced decision-making. The Vajont facility had operated successfully for over 3 years, with only minor geological incidents, building operational confidence that any geological hazards were manageable through existing procedures. This success history created a psychological framework that normalized minor geological events while building resistance to recognition of unprecedented hazard levels. Economic pressures contributed to these latent conditions through the facility's role as a critical component of regional power generation capacity. Operational decisions involved balancing safety considerations against economic impacts of reduced power generation or facility shutdown. The economic framework created systematic pressure toward continued operation unless clear, immediate safety threats were identified, biasing decision-making against precautionary measures based on uncertain geological information. The procedural framework for geological hazard response contained its own latent conditions through assumptions about hazard development timing and warning availability. Emergency procedures assumed that geological hazards would provide sufficient warning time for deliberate response, including consultation with geological experts, evaluation of alternatives, and implementation of protective measures. The procedures were optimized for gradual hazard development rather than rapid geological failure requiring immediate response. These multiple latent conditions existed independently throughout the facility's operational life, creating no immediate operational problems while establishing the framework for catastrophic failure under specific triggering conditions. Each condition represented reasonable engineering judgment and standard operational practice applied within a geological environment whose behavior exceeded the assumptions underlying those practices. The convergence of these latent conditions would create a situation where normal operational decisions triggered geological processes that existing monitoring and response systems could not adequately detect or manage. The human factors environment surrounding the Vajont Dam had evolved into a configuration that virtually guaranteed misinterpretation of geological warning signs when they eventually appeared. The systematic biases embedded within monitoring priorities, training emphasis, and decision-making procedures created multiple opportunities for normalizing geological hazard indicators rather than recognizing them as emergency warnings. Perfect execution of inadequate procedures had established conditions where professional competence could coexist with catastrophic blindness to developing geological hazards. The sequence that culminated in the October 9, 1963 disaster began not with a single triggering event, but through the convergence of seasonal conditions, operational decisions, and geological processes that had been developing throughout 1963. The initiating conditions emerged from routine reservoir management decisions that appeared entirely normal within the operational framework governing the facility, yet created stress patterns within the geological system that exceeded critical stability thresholds. Throughout September 1963, reservoir operations followed seasonal patterns designed to capture autumn precipitation while maintaining optimal power generation capacity for the approaching winter demand period. The operational strategy called for raising the reservoir to maximum pool elevation of 722.5 meters, reaching the highest water levels in the facility's operational history. This elevation target represented standard practice for maximizing storage capacity during high inflow periods, implemented according to established protocols that had governed successful operations since initial filling. The reservoir level increase proceeded systematically throughout September, reaching 710 meters by September 28 and approaching the planned maximum elevation by early October. These water level changes occurred within normal operational parameters and attracted no special attention from operational staff or engineering oversight personnel. The gradual elevation increase appeared to confirm the design assumption that the geological system could accommodate full reservoir utilization without significant stability impacts. However, the relationship between reservoir elevation and geological stress within Mount Toc was far more complex than the operational framework recognized. The limestone and marlstone geological sequence containing ancient clay layers responded to increasing groundwater pressure through mechanisms that remained undetectable using existing monitoring systems. The clay interlayers, subjected to increasing pore pressure as reservoir levels rose, began experiencing reduced effective stress that compromised their shear strength without producing observable surface effects. Precipitation patterns during late September and early October contributed additional stress to the geological system through mechanisms that operated independently of direct reservoir level effects. Heavy rainfall throughout the region increased groundwater levels within the slope mass, adding hydraulic pressure to geological formations already stressed by reservoir-induced groundwater changes. The combination of reservoir-induced and precipitation-induced groundwater pressure changes created cumulative stress conditions that exceeded the historical experience upon which operational procedures were based. The geological response to these combined stress conditions began manifesting through subtle indicators that existing monitoring systems could detect but not definitively interpret. Ground movement measurements recorded by the limited geological instrumentation showed increasing displacement rates during late September, with daily movement increments rising from previous background levels of millimeters per day to several centimeters per day by early October. These measurements indicated accelerating geological processes, but the monitoring framework provided no clear criteria for distinguishing between normal seasonal adjustment and failure precursors. Visual observations during this period recorded additional indicators of geological stress that fit within the normal range of expected slope adjustment. Surface cracking appeared in several locations on Mount Toc, while vegetation changes suggested subsurface water movement patterns different from previous seasonal cycles. Springs and seeps showed altered flow patterns, with some traditional water sources diminishing while new seepage appeared in previously dry locations. These observations, individually considered, fell within the expected range of seasonal geological variation. The critical divergence between operational reality and geological reality occurred during the first week of October, when accelerating slope movement rates crossed thresholds that should have triggered heightened monitoring and possible operational restrictions. However, the monitoring systems in place could measure movement rates, but provided no definitive guidance for interpreting movement significance or predicting failure timing. The geological data indicated accelerating instability but could not answer the operational question of when or whether catastrophic failure would occur. On October 8, geological monitoring recorded slope movement rates approaching 20 centimeters per day, representing a dramatic acceleration from early September baseline measurements. These movement rates clearly exceeded normal geological adjustment patterns and indicated active instability within the slope mass. However, the monitoring framework provided no clear protocol for translating these measurements into operational decisions regarding reservoir-level management or emergency response activation. The operational response to this geological information reflected the systematic ambiguities embedded within the monitoring and decision-making framework. Engineering personnel recognized that accelerating slope movement indicated potential instability, but existing procedures provided no clear criteria for determining whether the movement represented gradual slope adjustment or catastrophic failure precursors. The geological data suggested cause for concern, but could not provide the level of certainty required for major operational decisions such as emergency reservoir drawdown or facility evacuation. Communication between operational staff, engineering consultants, and regulatory authorities during this critical period reflected the systematic delays inherent in the decision-making framework. Geological observations required interpretation by specialized consultants, followed by consultation with operational management, regulatory notification, and coordination of any response measures. This communication sequence, designed to ensure proper consideration of complex technical factors, introduced time delays that proved incompatible with the geological emergency timeline. The decision-making framework confronted an impossible choice between operational certainty and geological uncertainty. The geological monitoring systems provided clear evidence of accelerating instability but could not predict failure timing with sufficient precision to guide emergency response. Operational procedures required clear, immediate threat identification before implementing major protective measures, but the geological system could not provide the certainty required within the procedural framework. On the evening of October 9, slope movement rates exceeded 100 centimeters per day, indicating geological conditions far beyond any previous operational experience. The monitoring data clearly showed accelerating failure, but the time interval between measurement recording, data interpretation, and potential response implementation exceeded the geological process timeline. The geological system was approaching catastrophic failure on a timescale measured in hours, while the operational response system was designed for deliberate decision-making measured in days or weeks. At 22:39 on October 9, 1963, approximately 270 million cubic meters of Mount Toqu's southern slope failed catastrophically, sliding into the Vajont reservoir in less than 45 seconds. The slope failure occurred along geological planes that had been identified during construction-era surveys, but whose failure potential under operational reservoir conditions had not been adequately assessed. The failure mechanism involved deep-seated movement along clay interlayers that had been gradually weakened by increasing pore pressure throughout the period of rising reservoir levels. The geological failure created immediate hydraulic conditions that exceeded all operational planning assumptions. The landslide mass displaced approximately 50 million cubic meters of reservoir water, generating waves that overtopped the dam by more than 100 meters while subjecting the structure to impact forces far exceeding design parameters. The dam itself performed exactly as its structural specifications demanded, absorbing tremendous impact forces without structural failure, but could not contain the geological forces that had been unleashed within the reservoir basin. The speed of geological failure eliminated any possibility of operational response once the final failure sequence began. The time interval between definitive failure recognition and catastrophic impact measured in minutes rather than the hours or days required for meaningful emergency response. The operational framework designed for deliberate engineering decisions proved completely inadequate for geological emergencies requiring immediate action. The initiating event sequence revealed the fundamental incompatibility between geological process timelines and operational decision-making frameworks. The geological system provided warning signs that were detectable through existing monitoring systems, but these warnings could not be interpreted with sufficient certainty or rapidity to enable effective operational response. Normal operational procedures, applied within their intended framework, create the conditions for catastrophic geological failure that existing emergency response systems could not prevent or mitigate. The divergence between instrument reality and geological reality had become absolute by October 9th. The facility's structural monitoring systems continued reporting normal dam performance, even as the geological system containing the reservoir approached catastrophic failure. The information architecture that provided precise data about engineered system behavior remained blind to geological processes that would ultimately determine the facility's fate and the safety of downstream populations. The catastrophic failure sequence of October 9, 1963, unfolded according to geological and hydraulic principles that operated independently of human intention or engineered control systems. The physics governing the landslide event and subsequent wave generation followed natural laws that had been inadequately incorporated into the facility's design and operational framework. Understanding the failure chain requires reconstructing the mechanical processes that transformed a slope stability problem into a hydraulic catastrophe that overwhelmed all engineered safety systems. The geological failure mechanism centered on deep-seated movement along pre-existing weakness planes within the Mount Toc limestone sequence. The mountain's geological structure consisted of alternating layers of competent limestone and weaker marlstone, with ancient clay seams that acted as potential sliding surfaces under specific stress conditions. These clay interlayers, formed through geological processes occurring millions of years before human intervention, possessed mechanical properties that made them susceptible to strength reduction under increasing pore pressure conditions. The relationship between reservoir water levels and slope stability operated through groundwater pressure mechanisms that remained largely invisible to surface observation. As reservoir levels rose throughout 1963, groundwater within the slope mass adjusted to new hydraulic boundary conditions, increasing pore pressure within the clay interlayers and reducing their effective stress. This process followed established principles of soil mechanics, where increasing pore pressure reduces the normal stress available for shear resistance along potential failure planes. The critical threshold for slope failure occurred when pore pressure within the clay layers reached levels sufficient to reduce effective stress below the minimum required for shear strength. This threshold represented a mechanical tipping point, where geological forces exceeded the material's resistance capacity, initiating irreversible movement along the failure plane. The timing of this threshold exceedance was determined by the rate of pore pressure increase, which was controlled by both reservoir level changes and regional precipitation patterns. Monitoring data from the weeks preceding failure showed accelerating displacement rates that reflected the approach to this critical threshold. Movement rates increased from millimeters per day in early September to several centimeters per day by late September, then accelerated dramatically to over 100 centimeters per day immediately before final failure. This acceleration pattern is characteristic of progressive slope failure, where increasing movement rates indicate approaching mechanical limits for slope stability. The final failure sequence began during the evening of October 9th, when pore pressure conditions finally exceeded the critical threshold for slope stability. The geological failure initiated along a deep-seated sliding surface that extended approximately 400 meters below the original ground surface, mobilizing a rock mass volume of approximately 270 million cubic meters. The failure plane orientation, dipping toward the reservoir at approximately 25 degrees, created optimal conditions for rapid sliding once movement began. The velocity of the landslide mass during its descent into the reservoir reached approximately 30 meters per second, representing kinetic energy levels far exceeding any reasonable design consideration for reservoir facilities. This velocity resulted from the steep failure plane geometry and the large mass involved, creating momentum that could not be arrested by friction or mechanical resistance once movement initiated. The landslide behaved as a massive projectile impacting the reservoir water surface with tremendous kinetic energy. The hydraulic effects of the landslide impact followed fluid mechanics principles that governed wave generation in confined water bodies. The sudden displacement of 270 million cubic meters of rock into the reservoir created an immediate volume displacement that exceeded the reservoir's capacity to accommodate the additional material. The kinetic energy of the moving landslide mass transferred directly into the reservoir water, generating wave motion that propagated throughout the confined reservoir basin. Wave generation occurred through multiple mechanisms that operated simultaneously during the landslide impact sequence. The initial contact between the landslide mass and water surface created a primary displacement wave that propagated across the reservoir. Secondary wave generation occurred as the landslide mass continued moving underwater, displacing additional water volume and creating complex wave interference patterns throughout the reservoir basin. The confined geometry of the Vajont reservoir created hydraulic conditions that amplified rather than dissipated the wave energy. Unlike open water wave propagation, where energy disperses radially and decreases with distance, the narrow reservoir geometry concentrated wave energy and prevented normal energy dissipation mechanisms. The canyon walls acted as waveguides that focused hydraulic energy toward the dam structure and reservoir outlets. The wave that overtopped the dam reached heights exceeding 100 meters above the dam crest, representing water velocities and volumes that surpassed all engineering design considerations. The wave height resulted from the combination of initial displacement volume, landslide kinetic energy transfer, and reservoir geometry effects that concentrated hydraulic energy at the dam location. The dam structure experienced impact forces estimated at over 4 million tons, far exceeding any conceivable design loading. Despite these enormous forces, the Vajont dam structure performed remarkably according to its engineering specifications. The concrete arch transferred the hydraulic loads through its geometric design, distributing impact forces into the canyon walls without catastrophic structural failure. The dam's survival under such extreme loading conditions demonstrated the excellence of its structural engineering, while highlighting the inadequacy of the geological assessment that failed to recognize the landslide hazard. The hydraulic energy that overtopped the dam carried approximately 50 million cubic meters of water into the Vajont Valley below, creating a flood wave that traveled at velocities approaching 70 kilometers per hour toward the downstream communities. The flood wave maintained destructive capacity over the entire 4-kilometer distance to Longarone, arriving approximately 4 minutes after the initial landslide impact. The wave height at Longarone exceeded 70 meters, creating flood conditions that no reasonable emergency preparation could have survived. The physics governing the downstream flood wave followed open-channel hydraulic principles that determined wave speed and attenuation characteristics. The steep gradient of the Vajont Valley maintained wave velocity over long distances, while the confined channel geometry prevented lateral spreading that might have reduced wave height. The flood wave behaved as a moving wall of water that maintained destructive force throughout its downstream travel. The mass balance calculations for the entire event sequence reveal the magnitude of the geological disruption that occurred within the reservoir basin. The landslide removed approximately 270 million cubic meters of rock from Mount Toc, while displacing roughly 50 million cubic meters of reservoir water downstream. The remaining reservoir capacity was reduced from 150 million cubic meters to less than 50 million cubic meters, fundamentally, altering the facility's hydraulic characteristics and eliminating its operational viability. The energy balance of the landslide event demonstrates the enormous forces involved in the geological failure sequence. The gravitational potential energy of the landslide mass converted to kinetic energy during the descent, then transferred to hydraulic energy within the reservoir water. The total energy release approached that of a small nuclear explosion, creating forces that no engineered structure could reasonably be expected to contain or control. The failure sequence revealed fundamental physical incompatibilities between geological energy release and engineered containment systems. The landslide represented a geological process operating on energy scales and time scales that exceeded the design framework for civil engineering structures. The event demonstrated that certain geological hazards exist beyond the practical limits of engineering control, requiring hazard avoidance rather than engineering mitigation. The mechanical analysis of the failure chain shows that the disaster resulted not from engineering incompetence, but from the application of engineering solutions to a geological problem that exceeded the assumptions underlying those solutions. The dam performed exactly as its structural specifications demanded, while the geological system behaved according to natural laws that had not been adequately incorporated into the engineering analysis. The failure occurred at the interface between human engineering and geological systems that operated according to incompatible physical principles. Post-failure analysis of the landslide debris revealed that the geological failure followed predictable mechanical patterns that could have been anticipated through appropriate geological assessment methods. The sliding surface orientation, failure volume, and velocity characteristics all conform to established principles of rock slope stability analysis. However, these analytical methods had not been applied to the Vajont site with sufficient sophistication to recognize the failure potential under operational reservoir conditions. The physics autopsy of the Vajont disaster demonstrates that the failure sequence was mechanically inevitable once critical pore pressure conditions were reached within the slope mass. The geological system responded to hydraulic loading according to natural laws that operated independently of human recognition or control. The engineering systems performed according to their design specifications while remaining powerless to influence the geological processes that ultimately determined the facility's fate. The immediate aftermath of the October 9 landslide created unprecedented operational conditions that challenged every aspect of emergency response planning and facility management. The geological event had fundamentally transformed the Vajont reservoir system, creating new hazard patterns and operational constraints that existing procedures could not adequately address. The period following the initial disaster revealed additional failure modes and response limitations that compounded the original catastrophe while demonstrating the inadequacy of emergency frameworks designed for conventional dam incidents. The first priority for emergency responders involved assessing the dam's structural integrity following impact forces that far exceeded any design consideration. Initial inspection teams arriving at the facility within hours of the landslide found the concrete arch structure remarkably intact despite having experienced hydraulic loading estimated at over 4 million tons. The dam had successfully transferred these enormous forces through its geometric design, distributing impact energy into the canyon walls without catastrophic structural failure. However, the facility's operational viability had been completely eliminated by the geological reconfiguration of the reservoir basin. The landslide debris had created a natural dam within the reservoir, blocking normal water flow patterns and creating new hydraulic conditions that posed ongoing hazards for downstream areas. The debris pile, rising nearly 200 meters above the original reservoir bottom, had effectively divided the water body into separate compartments with uncertain interconnection. This geological reconfiguration created the potential for additional slope failures as the debris mass adjusted to its new position, while also creating new flood hazards if the debris dam failed or was overtopped by future precipitation. Reservoir water level management became an immediate crisis as normal operational controls were rendered ineffective by the changed hydraulic conditions. The landslide had displaced the majority of stored water downstream, but significant volumes remained trapped behind the debris barrier with no predictable release mechanism. Traditional spillway and outlet systems were either damaged or inaccessible, eliminating normal methods for controlling water levels or releasing stored volumes. Emergency water management required improvised approaches, using equipment and methods outside standard operating procedures. The debris stability analysis presented ongoing hazards that emergency response teams were ill-equipped to evaluate. The landslide mass, consisting of fractured rock materials ranging from boulders to fine debris, had achieved a temporary equilibrium position that might not remain stable under changing conditions. Additional rainfall continued geological adjustment or human Intervention activities could trigger secondary slope failures within the debris pile, creating new downstream flood risks or releasing additional stored water volumes. Geological monitoring capabilities had been severely compromised by the landslide event, eliminating most instrumentation and observation points that might have provided information about continuing slope stability conditions. The instruments that survived the initial failure were located outside the primary slide area and provided limited information about ongoing geological processes within the affected zone. Emergency response teams were forced to rely on visual observation and rudimentary measurement techniques to assess ongoing geological hazards. The uncertainty regarding debris dam stability created impossible decision-making conditions for emergency management personnel. The debris barrier might remain stable indefinitely, providing natural flood control for the modified reservoir system. Alternatively, the debris could fail catastrophically, releasing trapped water volumes and creating secondary flooding downstream. The time frame for potential debris failure ranged from immediate to indefinite, providing no basis for definitive emergency planning or resource allocation decisions. Access to the disaster site created additional operational challenges as normal transportation routes had been destroyed or rendered impassable by the landslide and flood effects. Emergency response teams required helicopter transport to reach critical observation points, limiting the personnel and equipment that could be deployed for assessment and stabilization activities. The logistical constraints prevented deployment of heavy equipment or specialized geological monitoring instruments that might have provided better information about ongoing hazard conditions. Communication systems serving the facility had been extensively damaged, eliminating normal coordination capabilities between field personnel, emergency management centers, and technical support resources. Emergency responders were forced to establish improvised communication networks using portable equipment while operating under severe time pressure to assess multiple concurrent hazards. The communication limitations prevented effective coordination with geological experts and engineering consultants whose expertise was essential for evaluating the complex post-failure conditions. The downstream areas affected by the initial flood remained at risk for secondary flooding if the debris dam failed, or additional landslides occurred within the modified reservoir basin. Emergency evacuation of survivors and relief personnel created additional logistical challenges, while ongoing geological uncertainty made it impossible to determine safe areas for temporary shelter or staging operations. The emergency response framework was designed for discrete disaster events with definite conclusions, not ongoing geological hazards with indefinite resolution timelines. Weather conditions during the days following the disaster introduced additional complications, as autumn precipitation threatened to destabilize the debris pile while adding water volume to the trapped reservoir segments. Rainfall that would normally present no operational concern became a significant hazard factor given the uncertain stability of the landslide debris and the compromised state of water control systems. Meteorological monitoring became a critical component of ongoing hazard assessment, requiring integration with geological and hydraulic analysis in ways that existing protocols did not address. The psychological impact on emergency response personnel created additional operational challenges as the unprecedented nature of the disaster exceeded the training and experience base of most participants. Standard emergency procedures provided no guidance for geological disasters of this magnitude, forcing responders to improvise assessment and mitigation approaches while operating under extreme time pressure and uncertain safety conditions. The stress of operating outside established procedural frameworks while making decisions with life-or-death consequences affected judgment and coordination capabilities throughout the emergency response effort. Technical assessment of the facility's long-term status required expertise in geological engineering, structural analysis, and hydraulic engineering that was not readily available through normal emergency response channels. The complexity of the post-failure conditions exceeded the analytical capabilities of standard emergency assessment teams, requiring specialized consultation that introduced additional delays and communication challenges. The technical assessment process revealed that the facility could never be restored to operational status, eliminating its economic value while creating ongoing liability for hazard management. The legal and regulatory implications of the disaster created additional pressures that complicated technical decision-making throughout the emergency response period. Responsibility questions regarding the original failure, liability for downstream damages, and authority for ongoing hazard management decisions remained unresolved, while immediate safety decisions required implementation. The legal uncertainty prevented clear allocation of resources and decision-making authority, hampering effective coordination of emergency response activities. International attention focused on the disaster created additional pressures for rapid resolution that conflicted with the geological realities of the situation. Media coverage and political pressure demanded definitive statements about safety conditions and future hazard potential, while the technical assessment revealed fundamental uncertainties that could not be resolved through conventional engineering analysis. The pressure for public communication created systematic bias toward overconfident statements about safety conditions that were not supported by available technical information. The economic impact of the facility's destruction extended beyond direct replacement costs to include regional electrical power shortages, lost industrial production, and ongoing monitoring and safety costs that would continue indefinitely. The disaster had eliminated a critical component of regional power generation capacity, while creating ongoing liability for geological hazard management that would persist for decades. The economic analysis revealed that the full cost of the geological failure extended far beyond the immediate human casualties, to include economic disruption and ongoing risk management costs. The stabilization period following the Vajont disaster demonstrated the inadequacy of emergency response frameworks for geological catastrophes that exceeded conventional disaster planning assumptions. The event created ongoing hazard conditions that could not be resolved through standard engineering intervention, requiring indefinite monitoring and risk management that stretched beyond normal emergency response capabilities. The disaster had transitioned from an acute emergency to a chronic geological hazard that would require ongoing management for the foreseeable future. The lessons emerging from the stabilization period revealed fundamental limitations in the engineering approach to geological hazard management. Certain geological processes operate on energy scales and timescales that exceed practical engineering control, requiring hazard avoidance rather than engineering mitigation. The Vajont experience demonstrated that geological hazards can create failure conditions that persist indefinitely after the initial event, challenging assumptions about disaster recovery and facility restoration that underlie normal emergency planning frameworks. The forensic investigation that followed the Vajont disaster produced unprecedented documentation of catastrophic slope failure mechanics and revealed fundamental inadequacies in the geological assessment methods that had been considered state-of-the-art during the facility's design and construction. Physical evidence recovered from the disaster site, combined with detailed analysis of pre-failure monitoring data, established a comprehensive understanding of the failure mechanism while exposing systemic weaknesses in the engineering frameworks used for large-scale infrastructure projects in geologically complex environments. Post-disaster geological surveys confirmed that the landslide had followed a deep-seated failure plane located along ancient clay interlayers within the limestone sequence, exactly as soil mechanics theory would predict under the poor pressure conditions that had developed during 1963. Core drilling through the landslide debris revealed the geological structure of the failure plane, showing clay layers with reduced shear strength consistent with elevated pore pressure conditions. The physical evidence confirmed that the failure mechanism was mechanically predictable using established geological engineering principles, but only if those principles had been applied with appropriate sophistication during the original site assessment. Forensic analysis of the pre-failure monitoring data revealed a clear acceleration pattern in slope movement rates that provided unambiguous warning of impending catastrophic failure. Movement rates had increased exponentially during the final weeks, following patterns that geological engineering literature had established as characteristic of progressive slope failure approaching collapse. The monitoring data contained sufficient information to predict catastrophic failure, but the interpretation framework used by operational personnel could not translate the geological measurements into operational decisions within the required timeframe. The investigation of reservoir operation records during 1963 confirmed the critical role of water level management in triggering the geological failure sequence. The rapid rise to maximum pool elevation during September created groundwater pressure conditions within Mount Tauk that exceeded the historical range of geological stability for the clay inner layers. Hydraulic analysis demonstrated that the reservoir operation strategy had inadvertently created a controlled geological loading experiment that systematically reduced slope stability until catastrophic failure became inevitable. Physical examination of the dam structure itself provided remarkable confirmation of the structural engineering excellence that had characterized the project's design and construction. Despite experiencing impact forces estimated at over 4 million tons, the concrete arch showed minimal structural damage and retained its basic geometric configuration. The dam had successfully transferred the enormous hydraulic loads through its designed force paths, demonstrating that structural engineering principles had been correctly applied within their intended operational domain. However, the same forensic analysis revealed the fundamental conceptual limitation that had made the disaster inevitable despite engineering excellence. The dam had been designed as an isolated structural system rather than as a component within a broader geological system. The structural engineering analysis had treated the surrounding geology as a stable boundary condition, rather than recognizing the reservoir operation as an active geological loading system that could trigger large-scale instability. International geological engineering experts who participated in the forensic investigation concluded that the Vajont failure represented a predictable consequence of applying reservoir loading to a geologically unsuitable site, rather than an unforeseeable geological accident. The clay interlayers and slope geometry that controlled the failure mechanism were detectable using standard geological survey methods available during the 1950s construction period. The failure occurred not because the geological hazard was unrecognizable, but because the geological assessment framework used during site development was inadequate for evaluating reservoir-induced slope stability conditions. The forensic reconstruction of decision-making processes during the critical period preceding failure revealed systematic information processing failures that prevented effective response, despite adequate technical warning signs. The organizational structure that separated geological monitoring from operational decision-making created communication delays and interpretation ambiguities that proved incompatible with geological emergency response requirements. Technical information that clearly indicated approaching catastrophic failure could not be processed through administrative frameworks designed for routine operational decisions. Legal investigations conducted by Italian judicial authorities established criminal liability for several engineers and officials involved in the project's development and operation, concluding that professional negligence had contributed to the disaster. However, these legal conclusions conflicted with technical assessments that attributed the failure to systematic limitations in geological assessment methodology rather than individual professional incompetence. The legal framework's emphasis on individual responsibility obscured the more fundamental systemic issues that had enabled the disaster. The economic forensics revealed that the disaster's total cost exceeded 50 billion lire in 1963 currency, including direct damages, lost economic production, ongoing monitoring and safety costs, and legal settlement expenses. The economic analysis demonstrated that comprehensive geological assessment during the initial design phase would have cost a small fraction of the ultimate disaster expenses, providing overwhelming economic justification for more sophisticated geological evaluation methods in future large-scale infrastructure projects. International regulatory responses to the Vajont disaster established new requirements for geological hazard assessment in dam projects worldwide. The International Commission on Large Dams developed enhanced guidelines for slope stability analysis in reservoir areas, while national dam safety programs incorporated specific requirements for ongoing geological monitoring throughout facility operational life. These regulatory changes represented recognition that geological hazards required ongoing management rather than one-time assessment during site selection. The technical lessons extracted from the Vajont experience established fundamental principles for geological hazard management that challenged prevailing engineering confidence in technological solutions to geological problems. The disaster demonstrated that certain geological processes operate on energy scales that exceed practical engineering control, requiring hazard avoidance rather than engineering mitigation. This recognition forced fundamental changes in site selection criteria and operational protocols for large-scale infrastructure in geologically complex environments. Forensic analysis of similar geological conditions at other reservoir sites revealed that the specific combination of geological structure and reservoir geometry that characterized Vajont was not unique. Several existing and proposed reservoir projects showed comparable geological risk factors, requiring comprehensive stability re-evaluation using analytical methods that had been developed following the Vajont experience. The forensic investigation had identified a previously unrecognized category of geological hazard that affected the safety evaluation of numerous existing facilities. The psychological and sociological impacts of the disaster were documented through longitudinal studies of survivor populations in affected communities, revealing long-term effects that extended far beyond immediate physical damages. The unprecedented scale of the catastrophe and its association with technological failure rather than natural disaster created lasting trauma patterns that influenced regional attitudes toward large-scale infrastructure development. These psychological impacts represented hidden costs of the disaster that persisted for decades beyond the immediate event. Educational responses within engineering institutions worldwide incorporated Vajont case study materials into geological engineering curricula, establishing the disaster as a foundational example of the importance of comprehensive geological assessment in infrastructure projects. Engineering education programs developed specific course modules addressing the interaction between geological systems and engineered structures, emphasizing the limitations of engineering solutions when applied to inadequately understood geological conditions. The scientific legacy of the Vajont disaster included advancement in slope stability analysis methods, reservoir-induced seismicity research, and geological hazard assessment protocols that benefited infrastructure safety evaluation worldwide. Research programs initiated following the disaster produced analytical tools and assessment methods that significantly improved the capability for recognizing and managing geological hazards in large-scale infrastructure projects. The scientific advancement represented the primary positive outcome of the catastrophic failure experience. Long-term monitoring of the Vajont site continued for decades following the disaster, providing unique scientific data on post-failure geological adjustment and debris stability characteristics. The monitoring data contributed to understanding of large-scale slope failure recovery processes, while confirming that the geological reconfiguration created by the landslide was essentially permanent. The site remained a geological hazard that required ongoing management indefinitely, confirming that certain types of geological failure create persistent rather than temporary risk conditions. The ultimate lesson extracted from the comprehensive Vajont forensic investigation was that engineering excellence applied within inadequate conceptual frameworks can create systematic blindness to critical hazards that exceed the assumptions underlying those frameworks. The disaster resulted not from engineering incompetence, but from the confident application of excellent engineering within a geological assessment framework that was structurally incapable of recognizing the most significant hazard at the site. Perfect technical execution of an incomplete understanding had created the conditions for an unprecedented failure that challenged fundamental assumptions about the relationship between engineering control and geological systems. The Vajont disaster established that geological hazards exist beyond the practical limits of engineering mitigation, requiring recognition and avoidance rather than technological solution. This lesson forced fundamental reassessment of engineering confidence in technological solutions to geological problems, establishing principles of geological hazard management that continue to influence infrastructure safety evaluation practices worldwide. The disaster demonstrated that certain natural systems operate according to physical laws that exceed human engineering control, requiring humility and hazard avoidance in addition to technical sophistication.